Hello, in this video we are going to draw the molecular orbital diagrams for helium, hydrogen, lithium, beryllium, boron, carbon up to fluorine. So we are going to draw their molecular orbital diagrams. So let's continue. The main objective for molecular orbital diagram is to describe atoms, is to describe molecules in a way we describe atoms in terms of atomic orbitals and electron configuration. If we are given something like NO, how are we going to draw its molecular orbitals? Like how are we going to write its electron configuration? In this case, molecular orbital diagrams come in, or molecular orbital theory comes in. So now let's start. Starting with hydrogen, We know our hydrogen, it has an atomic number. If we look at hydrogen as a diatomic, then it becomes a molecule. So hydrogen has an atomic number of 1. So if we are to draw the electron configuration of hydrogen, the normal electron configuration of hydrogen is going to be 1s1. So now we are drawing the molecular orbital diagram for only the valence electrons. So hydrogen has 1 electron. So the valence electron of hydrogen, the valency of hydrogen is 1. So we have 1 electron. That means 1 electron. Since hydrogen is diatomic, then we are going to get 2 electrons. Like we have hydrogen, 1 hydrogen, and another hydrogen forming a bond to give us H2, which is hydrogen molecule. So now that means we are going to have 2 electrons. Simply, the valence electron that we get, we just multiply by 2. So we get 2 electrons. So that means let's draw the orbital diagram, the molecular orbital diagram. We are going to have 1s, another 1s for each of the hydrogen atom. This hydrogen has 1s orbital, this one also has 1s orbital. So 1s, 1s. So if 1s orbital of each of these hydrogen comes together, they are going to form molecular orbitals. They are going to form 2 molecular orbitals, the bonding and the anti-bonding. So the bonding is going to be here and the anti-bonding here. So that means 1s orbital of hydrogen and this 1s orbital of this hydrogen coming together to form a molecular orbital. So each hydrogen has 1 electron. So let's fill it singly. This hydrogen has 1 electron in its 1s orbital, and this one too also has 1 electron in its 1s orbital. So after this, the orbitals are going to overlap to give us these 2 orbitals, which is sigma 1s orbital, indicating that it is a bonding orbital, and sigma asterisk 1s orbital. This star here is indicating that this one is an anti-bonding orbital. So that means, we have a total of 2 electrons. When they come together, we have 2 electrons in their molecular orbital. So let's start filling. Filling it, we fill the bonding orbital fully before we fill the anti-bonding orbital. So now it is 2 electrons. We have 2 electrons. So let's start filling. You have 1, 2. So this is a molecular orbital diagram for hydrogen. So one thing we will do after drawing the molecular orbital diagram is to write the electron configuration. Write the electron configuration. And then also to calculate for the bond order of the molecule. So let's calculate for bond order of this molecule. Let's calculate for the bond order of this molecule. Hydrogen, the formula for bond order is equal to number of bonding electron minus number of anti-bonding electron, or half. So the bond order is equal to half of the number of bonding electrons minus number of anti-bonding electrons. So if we look at the molecular diagram for hydrogen, how many electrons we have in the bonding orbital? So this is the bonding orbital and this is the anti-bonding orbital. So in the bonding orbital, we have 2 electrons. Like I said earlier, the orbital with asterisk means it is an anti-bonding orbital. So we have 2 electrons in the bonding orbital. So this will give us 2 minus the number of electrons in the anti-bonding orbital. This is the anti-bonding orbital for hydrogen here, for hydrogen molecule, sorry. So we have 0. There's no electron there. Multiply by half. So at the end of the day, we are going to get 2 out of 2, which is equal 1. So what is meant by the bond order? Like, what does the bond order represent? The bond order means that generally hydrogen will prefer to form a single bond in molecules. Like for instance, it is very difficult to see oxygen like double bonded to hydrogen like this. It is very difficult. So mostly you see hydrogen bonding in molecule like forming only single bond. So we're done with the bond order. Now let's write the electron configuration of this molecule, hydrogen molecule. So now the electron configuration, we have 1s. We are going to base on the molecular orbital. So we have sigma 1s. We also have sigma asterisk 1s. How many electrons do we have in sigma 1s orbital? We have 2 electrons. So we write it here. In sigma asterisk 1s orbital, what do we have? The anti-bonding orbital, what do we have? We have nothing, like 0. So we are done for hydrogen. Let's do for helium. We know our helium has an atomic number of 2. So let's write the electron configuration of helium. We have 1s2. So that is all for helium, 1s2. Now, what is the valence electron here? How many valence electrons does helium has? We have 2. So 2 electrons. Like I told you earlier, since we are considering helium as a molecule, we multiply the number of valence electrons by 2, giving us a total of 4 electrons. And now we draw the molecular orbital diagram for helium. Let me change another. Let me take this. So let's draw the molecular orbital diagram for helium. So let's start with the 1s orbital because we are taking only the. Sorry, let me write this one here. Helium as diatomic. It was 1s2. So we have 2 valence electrons. So multiply by 2 to give us 4 electrons. Since we are looking at helium at molecule, that means 2 heliums coming together to form helium molecule. So now let's draw the molecular orbital diagram. For the molecular orbital diagram, we have one of the helium atom here, one helium atom here. So 1s of this helium atom, when they overlap, when they form molecule, they are going to give us bonding orbital and anti-bonding orbital. So we have sigma 1s, which is the bonding orbital, and sigma star 1s, which is the anti-bonding orbital. So now each helium here has 2 electrons in each valence shell. So this helium has 2 electrons. Let's fill it 1, 2, 1, 2. And in the molecular orbital, each helium will bring 2 electrons. So forming a total of 4 electrons. That's why we multiply here by 2. So now let's fold the molecular orbital with the electrons. We have a total number of 4 electrons. So we fill starting from the bonding to anti-bonding. So 1, 2, 3, 4. We are done. This is a molecular orbital diagram for helium. So now let's calculate for the bond order of helium. Calculating for bond order of helium. So, but don't forget to indicate your energy diagram, like your energy direction of your energy flow. So let's calculate for the bond order. Bond order equal total number of half of bonding electron minus non-bonding electrons. So how many bonding electrons we have here? The non-bonding is the same as anti-bonding electrons. So the bonding electrons in the if you are looking at the bonding electrons, we look at the bonding orbital and we have the anti-bonding orbital. So bonding electrons are to be in bonding bonding electrons are to be in bonding orbital, and non-bonding electrons are to be in non-bonding orbital. So now let's write it here. We have half of how many bonding electrons we have? 1, 2 minus non-bonding electron 1, 2, 2. So at the end of the day, we are going to get 0. So there's one thing you need to know about this. The bond order of helium is 0. What does it indicate? This shows that generally the molecular orbital theory, according to the molecular orbital theory, helium does not exist. Like helium molecule does not exist. That is why we got a bond order of 0. That means there is no way we have H2 bonding to He bonding to He. Well, that's it. So now what next? Let's write the electron configuration of this. So electron configuration, we have sigma 1s and we have 2 electrons there, and sigma asterisk 1s, we have 2 electrons there. So this is the electron configuration of helium molecule, and it has a bond order of 0. So now let's continue. Let's continue. We are now going to lithium. Lithium as a diatomic. Does it exist? So what is the atomic number of lithium? 3. So let's write the electron configuration of lithium. That is the first thing to do, so that we get to know the valence electrons, and then we deal with that. So electron configuration of lithium is going to be 1s. How many electrons do we have? 3. 2. 1s orbital is 4, so we go to 2s. Notice that the s orbital can accommodate only 2 electrons, maximum of 2 electrons. So 1. So what is our valence electron here? Sorry, our valence shell here. Our valence shell is a 2s orbital. We can draw the molecular orbital diagram of lithium starting from 1s up to 2s. There's nothing is going to change. The only thing is that molecular orbital diagram is going to be bulky. So that is why we only deal with the valence, the valence electrons. So now we are not going to, let's start from 1s and see. So we are going to have we have 1s orbital of each lithium. Sorry. And then the 2s orbital. So if they overlap, if 2s orbital overlap, they will form 2 molecular orbitals, the bonding and the anti-bonding. If 1s orbital and 1s orbital overlap, they will form 2 molecular orbital. Don't forget this, 2 molecular orbital. That is the bonding and the anti-bonding. So here we have sigma 1s, and here sigma star 1s, which indicates the anti-bonding. Here we have sigma 2s orbital, and here sigma asterisk 2s orbital. So we know each 1s orbital is fully fold. So let's fold this 1s orbital 1, 2, 1, 2. Because if we were to take everything into consideration, we have 2 electrons here, 1 electron here, so 3 electrons. So we multiply by 2 to get 6 electrons. So for the 2s orbital, each of them has 1 electron. So 1, 1. We have a total of 6 electrons. Then we now start filling our molecular orbitals. So let's start 1, 2, 3, 4, 5, 6. So you see, we are done now. So let's look at the bond order for this and for this molecule. So we know our bond order to be equal to total number of bonding electrons, half of bonding electrons minus non-bonding electrons. So how many bonding electrons we have here? 1, 2, 3, 4. We are not taking this, the one with the star, because it's an anti-bonding orbital. So 1, 2, 3, 4. We have 4 electrons in the bonding orbital minus how many electrons we have in the anti-bonding orbital? We have 1, 2, 2. At the end of the day, we are going to get half of 2, which is equal to 1. So this is the bond order for lithium molecule. Mostly, we have to, you see, our orbital diagram becomes bulky. So that is why we sometimes take only that of the outermost shell. So if we were to take that of the outermost shell, which is 2s orbital, we know our lithium 1s2, 2s1. Only the outermost orbital will give us 1 electron. Since we have 2 of them multiplied by 2, we are going to get 2 electrons. And we can now draw the molecular orbital diagram for this, for lithium. So we're going to get 1, 2, 3, 4. So now since we are doing for the valence, which is a 2s orbital, we start with the 2s orbital. 2s orbital. When 2s and 2s overlap, they give us 2 molecular orbitals, which is the bonding and the anti-bonding. So we have sigma 2s and sigma anti-2s. So each 2s has an electron of 1. You can see from here. So each 2s has an electron of 1. So 1, 1. We only take the total number of electrons in the conjugate when we are filling the molecular orbital. And notice that the bonding orbital must be followed by the anti-bonding. So we have 2 electrons, only 2 electrons. So 1, 2. So at the end of the day, you can see that if we are calculating for our bond order, we're going to look at the number of electrons in the bonding orbital, which is 2, minus number of electrons in the anti-bonding orbital, which is 0, multiplied by half. It's also going to give us 1. So that is why mostly we have to deal with the valence electrons, like the valence shell. Because if we add the 1s orbital, it's going to make everything bulky. So we deal with the valence 1. So let's go. I just want us to know the reason why we have to be taking the valence orbital, because it's going to make the diagram bulky. And at the end of the day, the 1s orbital, the anti and the bonding orbital are going to cancel out. So let's continue. Let's now do for beryllium. Beryllium, sorry, has an atomic number of what? What's the atomic number of beryllium? 4. So 4. Let's write the electron configuration of beryllium. So we have 1s2 and then 2s2. So total number of 4 electrons. Let's take only the valence orbital into consideration, which is 2s. How many electrons we have? 2. We multiply by 2 to get 4. So 4 electrons. And I told you the reason why we are multiplying by 2. We have 2 beryllium atoms coming together to give us beryllium molecule. So we multiply the valence electron by 2, which will encounter for both of the beryllium atoms. So now let's write the electron configuration for beryllium. We have 1. This is for the 2s, 2s. And when they overlap, we form sigma 2s and sigma asterisk 2s. So each 2s has 2 electrons. So let's fold them 1, 2, 1, 2. Now we are filling the molecular orbital. The molecular orbital, we take all the electrons into consideration, because why do we have 2 electrons here? Because at the end of the day, 2s brought 2 electrons, and these 2s also brought 2 electrons. We're going to get 4 electrons. So let's fill the molecular orbital diagram. So 1, 2, 3, 4. So now let's write the bond order for beryllium. Bond order is equal to half of bonding electron minus non-bonding electron. So how many bonding electrons we have here? With the bonding orbital, we have bonding electrons in bonding orbital. So 1, 2, 2 minus. How many electrons do we have in the anti-bonding? 1, 2 anti-bonding, indicated by the star. We have 2. So at the end of the day, we are going to get 2 half multiplied by 0, which is also going to give us 0. So the bond order for beryllium molecule is 0. This means that according to molecular orbital theory, since we have a bond order of 0, it means beryllium molecule does not exist. Generally, it means there's no way we have Be bonding to Be. So let's write the electron configuration. In writing the electron configuration, since we did not include that of the 1s orbital, the core electrons, we call them the core electrons. So let's represent that one by configuration. Let's represent the 1s orbital by kk, or you can also decide to bring it. So after the core electron, we start with the 2s orbital. We have sigma 2s with 2 electrons, sigma asterisk 2s with 2 electrons. Or you can bring in the core electron. The core electron is just sigma 1s 2 electrons, sigma asterisk 1s 2 electrons. Then now start with the 2s orbital, which is sigma 2s2 and sigma asterisk 2s2. So in any way that you write it, it will be okay. So now let's write the electron configuration for the molecular orbital diagram for boron. Boron. If boron is a diatomic, then boron, what is the atomic number of boron? Is 5. So let's write the electron configuration of boron. We are going to have 1s2, 2s2. Then you see, we cannot write 2s3 because the maximum number of electrons that the s orbital can accommodate is 2. So now we just enter into 2p orbital, which is 1. So total number of 5 electrons. So 1, 2, 3, 4, 5. And I told you earlier, we are only going to take the outermost orbitals into consideration. So starting from 2, in this case, our energy diagram is, we are going in with our energy diagram, we are going to include 2p orbitals. So what is the total number of electrons in the outermost shell? Or how many valence electrons we have for boron molecule? So 2, 1, which is 3. Like I told you, I will multiply by 2 because we have 2 boron atoms coming together to give us B2. So 3 by 2 is going to give us a total number of 6 electrons. So let's now draw a molecular orbital diagram. So we have 2s, 2s, and we have a 2p, 2p, 2p orbital, 2p, 2s, 2s. Don't forget, we are not starting with the 1s because at the end of the day, the 1s is going to cancel out. But if we are writing the electron configuration, we take it into consideration. So if 2s and 2s orbital overlap, we are going to get two molecular orbitals, which is the bonding and the anti-bonding. If 2p orbitals overlap, we are going to get two kind of molecular orbitals, which is the bonding and the anti-bonding. In this, the bonding will be here. Bonding, sorry, I didn't write this straight. Bonding, 3 orbitals. We have one anti-bonding. So note this this diagram very well. So here we have a 2 pi x orbital, 2 pi y orbital, and sigma, 2 pi orbital. This one you can, let's say pi, I'm coming, pi 2p is pi rather pi 2p, pi 2p. You can bring the x and y here. So pi 2p. And here too, we get a pi asterisk 2p, which is the x here. And then pi asterisk 2p, 2py, 2px, 2py. I feel like drawing this again. Let me draw it here. So 1, 2. So our 2p here, our 2p here, 2s, 2s, sigma 2s, sigma star 2s, pi 2p x, pi 2p y, and sigma 2p. You can see, or you can decide to leave it. So our pi 2p x asterisk anti-molecular orbital, anti-bonding molecular orbital. So pi asterisk 2p y, and sigma asterisk 2p. I'm sorry, it seems like this one is, let me think it this way. So in the p2s orbital, each 2s orbital has a total number of 2 electrons. Can you see that? So these 2s orbital have 2 electrons, 1, 2, 1, 2. And the 2p orbital, we have only 1 electron. Failing the 2p orbital, you start from here and to this place. So this one you start here, and this one starts inside, going outside. So we have a total number of 6 electrons. So let's fill the molecular orbital diagram. So we have 1, 2, 3, 4, 5, 6. For the 2py and 2px, we fold them single when they are full before we go to the sigma 2p orbital. I think that is clear. So now, I'm very sorry, this is very messy, but I'll make sure that we will repeat the same problem again. So now let's write the bond. Let's calculate for the bond order. The bond order is going to be the number of bonding electrons. This is a bonding orbital. This is anti. This is bonding. So 1, 2, 3, 4. We have total number of 4 electrons, minus. And the anti-bonding orbital, how many electrons we have there? This is the only anti-bonding orbital we have here. For these ones, the electrons do not reach here. So there's no electron here. So just forget it. We have 2 here. So at the end of the day, we are going to have half of 2, which is going to give us 1. So boron has a bond order of 1, which means generally boron will prefer to form a single bond. So let's write the electron configuration of boron. Like I told you earlier, we can represent the 1s orbital since it's not included. We are not by kk. Since we didn't include it in the diagram. So we have now sigma 2s orbital. So sigma 2s. So sigma 2s with 2 electrons. I have sigma star 2s with 2 electrons. And we have pi 2py with 1 electron, and pi 2px with 1 electron. So that's it for this. Let's continue. We are done with boron. So let's draw molecular orbital diagram for carbon. Molecular orbital diagram for carbon if it is diatomic. So what is the atomic number of carbon? Carbon has 6. Carbon is 6. Atomic number for carbon is 6. Sorry. Let's write the electron configuration of carbon. We have 1s, 2, 6 electrons, 2s, 2, that is 4 electrons, 2p, 2, that is 6 electrons. So we are taking the valence orbitals into consideration. So 2s and 2p, how many electrons we have in 2s? 2, in 2p, 2. So a total of 4. We multiply it by 2 since 2 carbon atoms came together to form carbon molecule. So we are going to get 8 electrons. So we now have 8 electrons for carbon. So let's draw the molecular orbital diagram for carbon. So we are going to start with the from 2s to 2p. So let me draw this neatly so that we don't get the same problem. So let me say 2p, when 2p comes together, we get this, and then 2s coming together to give us this, and then the entire molecular orbital for 2p. So we have our 2p here, and this is our 2s, our sigma 2s, our sigma star 2s. For this pi 2px, pi 2py, we can just represent it by pi 2p, like pi 2p orbital, pi 2p orbital, and here sigma 2p orbital. But if you also want to indicate the x and y, this is also okay, no problem with that. So here we are going to have pi star 2p orbital, and then sigma star 2p orbital. So in the 2s orbital, how many electrons we have? Each 2s orbital has 2 electrons. So this one has 2 electrons. This also has 2 electrons. 2p orbital has what? 2 electrons. I told you earlier, this one, when you are filling, you start filling into outside. Like, let me tell you, let's start from here. For this, you start from left to right. Like, you always start from left to right, left to right. So 1, 2, singly before pairing up. You have to fill each orbital singly before you start pairing up. So left to right, left to right. Each p orbital has 2 electrons. Like you can see here, each 2p orbital has 2 electrons. So now let's fill the molecular orbital. The molecular orbital we have, if we are filling the molecular orbital, we take the total number of electrons in the conjugate, like I told you earlier. So we have 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So the pi 2p has to be fully full before we go to the sigma 2 pi. So let's calculate for our bond order. Sorry, don't forget to indicate your energy diagram, like the direction of your energy flow. So the bond order is going to be how many electrons we have in bonding? 1, 2, 3, 4, 5, 6. Half of 6 minus anti-bonding. And the anti-bonding we have is here. So 2. So it's going to give us 4 out of 2, which is 2. So the bond order for carbon is 2. So that's why carbon prefer to form 2 bonds, like in molecules. Like you can have carbon bond, hydrogen, and those stuff. Carbon will always prefer to form a bond of 2, 4. So Let's write the electron configuration. We write KK indicating the core orbital, which is 1s. So we have our sigma 2s with 2 electrons, sigma star 2s with 2 electrons, and then we have we can just write pi 2p with 4 electrons. This is also accepted. In case that it is expanded to pi 2px and pi 2py, is also the same. So 2, 2. You can just write it like this. So we are done with carbon. Let's write that of nitrogen. Nitrogen has an atomic number of what? What's the atomic number of nitrogen? 7, right? So 7. So 1s2, 2s2, 2p3. So 2p3, let's write the orbital diagram. 1, 2, 3, 1, 2, 3, 2p, 2p. Two S, sigma 2s, and pi 2p, sigma 2p. That's it. Each 2s orbital has 2 electrons. So 1, 2, 1, 2. And the p orbital has 3 electrons. Each of them has 3 electrons. So, sorry, let's calculate for vanishing. So 2 plus 3, 5 by 2, total number of 10 electrons. So p has 3 orbitals. P orbitals has 3 electrons, each of them. So 1, 2, 3. And here 1, 2, 3. We have a total number of 10 electrons. Let's fill our molecular orbital. Our molecular orbital is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our bond order is going to be total number of bonding electrons, which is 1, 2, 3, 4, 5, 6, 7, 8. 8 minus anti-bonding, 1, 2, which is 2, half of it. So we're going to get 6, half of 6, which is equal to 3. So nitrogen, bond order for nitrogen is equal to 3. That's why nitrogen will prefer to form triple bond. So let's write the electron configuration of nitrogen molecule. So configuration, we have KK for the core orbital. So we have sigma 2s 2, sigma star 2s2, and we have our pi 2p to be 1, 2, 3, 4, and sigma 2 pi to be 2. Like I told you, you can represent the 2p or x, pi 2px, pi 2py this way. But for the sigma, you have to indicate it this way. So that is it for nitrogen. Let's go for oxygen. For oxygen, I already drew the molecular orbital diagram, so all we have to do is to just start filling. So oxygen has an atomic number of 8. Mind you, when we're drawing the molecular orbital diagram for all of them, you could see that we have, you could see for the 2p, like for the bonding orbital of 2p orbital, you could see that the 2 pi 2p comes first before the sigma 2p. But here, you are going to see the sigma 2p coming first before the pi 2p. But for the anti-bonding, no problem with this. Pi asterisk, sigma asterisk, 2p. For the anti-bonding, no problem with that. So why this? What you have to know is that if we have if an element, or if the atomic number of the molecule that we are taking into consideration is less than, let's say atomic number is greater than or equal to 8, the 2p bonding orbital is no more going to be like this, like pi 2p, sigma 2p. It's going to turn upside down, in which the sigma will come first before the 2 pi, like this. We have sigma 2p, sigma 2p before the pi 2p. So this is the difference. So now let's continue with our oxygen. Our oxygen has a total number of 8 electrons. So let's write the electron configuration for oxygen. So 1s2, 2s2, 1s2, 2s2, 2p, 2p, this is for 2p4. So now you can see for the valence, for our valence orbitals, 2s, each of them has 2 electrons. So 2s, 2s, sigma 2s, sigma star 2s, and this is our 2p orbital. So 2s has 2 electrons each. So 1, 2, 1, 2. And for the 2p, 4, 4. So we start filling from left to right. 1, 2, 3. Since it is full, then we start pairing up 2. 1, 2, 3, then 4. Each of the p orbital has 4 electrons. So this p orbital 4 and this 4. So when they overlap, they give us this. So this one, let's fill our molecular orbital. So for our valence electron, we are going to have 4 plus 2, which is what? 4, 5, 6. So 6 by 2, going to give us a total number of 12 electrons. Like always, don't forget to indicate your energy, the direction of your energy flow. So we have 12 electrons. Let's start filling. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now let's calculate for our bond order. Our bond order equal total number of bonding electrons minus, half of total number of bonding electrons minus total number of anti-bonding electrons. This is our bonding orbital. So we have bonding electrons, bonding orbital. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 minus anti-bonding. Anti-bonding is usually, the orbital is usually indicated by star. So it's simple to identify. So we have here 1, 2, 3, 4, 4. So at the end of the day, we are going to get 6, half of 6, which is 3. So the bond order for oxygen is 3. So now let's write the electron configuration for oxygen. So we can represent the core orbital by kk. And now we start with sigma 2s2. So sigma 2s, 2. And sigma 2 as sigma asterisk 2s2, sigma 2s2, sigma star 2s2. And now we have a sigma 2p. So sigma 2p2, and this one pi 2p 1, 2, 3, 4, 4, and this one pi asterisk 2p2. We have 1 electron in each of the anti-bonding orbital of the pi 2p orbital. So that's it for oxygen. So now let's do for now for fluorine. What is the atomic number of fluorine? Fluorine has an atomic number of 9. So that means fluorine has an atomic number of 9. So let's write the electron configuration. 1s2, 2s2, 2p, 2p what? 5. So our total number of electrons in the valence shell is 5, 6, 7. 7 by 2 giving us 14 electrons. So at the end of the day, we are going to have 14 electrons in the molecular orbital diagram, not the individual atomic orbital. So this is a 2s, 2s, 2p, 2p, pi star 2p, sigma star 2p. And this is a sigma 2s, sigma anti like 2s, and our sigma 2p, and our pi 2p. I think that's okay. Yes. So now each of the 2s orbital has 2 electrons. So now 2s electron, this one has 1, 2, this one also 1, 2. And then for the 2p orbital, each of them has 5 electrons. So this 2p has 5 electrons. This one also 5 electrons. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think that is okay. So now let's fill our molecular orbital. When they come to overlap, we have 14 electrons. Each of the 14 electrons, let's start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we are done. Let's calculate for bond order. Let's calculate for the bond order of this molecule. So the bond order, which is BO, half bonding minus 1 bonding. Should I write the formula fully? I think you will be okay. So what is the total number of electrons do you have in the bonding orbital? This is the bonding orbital 1, 2, 3, 4, 5, 6, 7, 8. You have 8 electrons in the bonding orbitals. So 8 minus the anti-bonding orbitals. How many electrons do we have there? You have 1, 2, 3, 4, 5, 6. So 6. So then we're going to get half of 2, which is equal to 1. So fluorine, we prefer forming single bond according to the molecular orbital diagram. So now let's write the electron configuration for fluorine. Hope you can see. So we have, let's represent this core. Sure. Then we have a sigma 2s with 2 electrons, sigma star 2s with 2 electrons, and then 2 how do you call it? Sigma 2p. I think in writing this sigma 2p with 2 electrons. You also have a pi 2p with 4 electrons. Pi 2p with 4 electrons. And we have a pi asterisk with how many electrons? 1, 2, 3, 4, 4 electrons too. So pi star 2p 4 electrons. I think that's it for this video. And then one thing you can be asked to is you can be asked to see whether the molecule is diatomic or is diamagnetic or paramagnetic. So for paramagnetic, you have to tell whether the molecule is paramagnetic or diamagnetic. Look straight into the molecular orbitals. Look at the molecular orbital. If we see any unpaired electron, that means it becomes a paramagnetic. So diamagnetic means they are not attracted by a magnet. Like diamagnetic materials are weakly attracted by magnet, and then diamagnetic materials are weakly repelled by magnet because they have paired electrons. So the paired electron cancel their magnetic diamagnetic materials are weakly repelled by magnetic force because all the electrons are paired and their magnetic moment cancel out. Since the electrons are paired, their magnetic moment cancels out. So if you see in the molecular orbital that we have unpaired molecular orbital, that means it is paramagnetic, that is weakly attracted by magnet. And if the electrons in the molecular orbital are all paired, then you get diamagnetic. That means the molecule is diamagnetic. That means it is weakly repelled by a magnetic force. So let's look at fluorine for instance. Is it diamagnetic or paramagnetic? Looking at its molecular orbital, paired. The last one too are also paired. That means fluorine is diamagnetic. That means it is weakly repelled by magnetic force. Weakly repelled by magnetic force. So let's look at carbon. What do we have for carbon? When we drew the molecular orbital of carbon, like you could see that the molecular orbital diagram of carbon, you could see that we have all the electrons are paired in the molecular orbital. So in this case, carbon is diamagnetic. So that's it for this video, and thank you for watching. And don't forget to subscribe to my channel. I promise I will do better. Then I'll have other videos too on coordination chemistry, so you can check them out. So my next video is about heteroatomic molecules. Like if we have NO, how are you going to draw the molecular diagram for this? Or NO plus, how are you going to draw the molecular diagram for this? So I have another video on this. Thank you.